afternoon everyone. So today in this session we are going to work on analysis and visualization of flood hazards. Okay, so think like if you want to analyze a flood hazard extent, like how much an area is being flooded, you need data set to analyze the flood hazard extent. So the data sets also like before the occurrence of flood, how the area is like, and after the area got flooded, how the area got changed. Okay, if you have pre-data and also post-data, then you can analyze how the area has been changed due to the floods, right? So we need to consider pre-flood data and also post-flood data. Okay, so that data we are considering as satellite images. So satellite images we have a number of types like Landsat images, Sentinel data, MODIS and all like that. So among the available satellite images, we need to select the satellite image that is best suitable for our analysis purpose. So as we are working with flood analysis, we will take Sentinel-1 satellite images. Okay, why? Because Sentinel-1 uses radar pulses. So it emits radar signals, and when they hit the target or ground object, they'll reflect back. So during the rainy season or precipitation, when the precipitation is occurring, the atmosphere will be covered with clouds. So whatever the light, it should penetrate through the clouds. So Sentinel allows the radar data to penetrate to the clouds. For this purpose, we will consider Sentinel-1 satellite images. And also Sentinel-1 data is an active sensor, like it can operate throughout day and night. So we get complete coverage of the area throughout 24 hours. So we are considering Sentinel-1 images. And now I will explain in brief what is the process that we are going to do to analyze these flood hazards. After that we will work on it. Okay. So after selecting the satellite images, we cannot directly analyze them to visualize the floods. So before analysis, we need to perform some pre-processing of the satellite images. So pre-processing means the satellite images may have some distortions or noise within them. So we need to remove all the distortions before using them for the analysis purpose. Okay, so this pre-processing, removing all the noise or any distortions and applying their exact geographical locations, all this processing will be considered as pre-processing of satellite images. Okay, this step we will do using a software called SNAP, Sentinel Application Platform. Okay, so after the pre-processing from SNAP, we will get the exact data that is required for analysis purpose. So that data we will analyze using QGIS. QGIS is Quantum Geographic Information System. Okay, so using that software, we will analyze how much area got flooded, how the impact is. Everything we can analyze using that QGIS software. So this is the overall process that we are going to do in this session. Okay, so first of all, I hope that everyone have downloaded the data sets. I'll show you how to download them now. As it takes time, we told you to download them earlier. Okay. So as I told you, we are working with Sentinel-1 images. Okay, they will be provided by European Space Agency ESA, Copernicus. So you just type ESA Copernicus in the search bar. Here you have explore data. So once you directed to this page, you can log in. For first time users, you need to register. So click on the Sentinel Hub. you can register. It is a simple step, like after giving all your details and email ID, an activation link will be sent to your email. Upon clicking that link, you will be directed to the dashboard, like where you can access the data. Okay, fill in all the fields and accept the terms and conditions, and then click on register. It's just a simple step. You will get an activation link to the email. Would you like to do it now, or shall I show how to download? Are you trying to register now? Yes, try. Please try to register and check your email. Click on the activation link. If anyone is facing problem, please let me know. Okay, shall I proceed to login? You're not going to download any dataset now because it takes too much of time. You have already downloaded the datasets, right? So just I will show you how to download. So once you log in, this is how the page looks, and you can go to browse the datasets. is how the page looks like, where you can browse the data sets. So if you zoom out, you can see the patches where this Sentinel-1 data is available. Sentinel data is available, okay. So go to search and type the name of the place or study area that you are focused to analyze. So for this tutorial, we are going to work with a flood that was occurred in Ernakulam, Kerala during August 2018. So I am selecting that location. Okay, so here is the place. So we need to search the available data set tiles that were covering this area. So for your reference, you can place this location mark here. So this is the area of our interest. Okay, now we need to find data sets of particular date range. So I am saying that the flood has occurred during August 2018. So we need two data sets, one with all before the occurrence of flood and one data set just after it got flooded. Okay, actually from June 2018 onwards, there is heavy precipitation in that region. So we are going to consider pre-flood data during the end of May. And the peak flood has occurred in second and third week of August. So the last week of August can be taken as post-flood satellite image. So we are selecting Sentinel level 1 ground. So here there are various options, like the first one is raw data which is unprocessed, and this is a complex data format. This is ground range deduction. So we are going to select level 1 GRD. So here is the time range. So I have given these date ranges. Now let us find the available tiles. If you place cursor on a tile, it represents at what time stamp it is available. See here, this one is May 29th. So this is June 10th. So like that, you need to select the particular date which is before all the precipitation has occurred. So this August 21st, 2018 can be considered as post-flood satellite image. So you can directly click on the download link that is available. So before that, check whether the tile lies in your study area or not. So here the green colored one is the tile. So you can directly click on the download link. So it starts downloading. It takes a longer time to download. So I am not downloading it now. Okay. Everyone clear till now? similar way, you need to download the satellite image before it got flooded. Okay. So now let us move to the data sets that we have. So this is the folder that we have shared in the Google Drive. So if you observe, these two are the data sets. Okay. You can clearly see the timestamp here. 2018 May 17th. And the next one is 2018 August 21. Okay. So this is before all the precipitation has started. And the next one is post flood. So we got the satellite images. So the next step is to pre-process these satellite images. So we are pre-processing them using Snap. So open this Snap software. Okay. File, open product. So go to the location where you have downloaded. You can directly give the file without extracting. First, let us work with the first one, like 17th of May. So open that file. You can see it here. Is everyone able to open the file in Snap? Okay. Now shall we proceed?
Make sure that everything is different things.
Okay, so once you have added the data here in Snap, if you see here the bands, you can see the 4 available bands. So here the VV, VH all corresponds to the polarization. So polarization is like how the electric field is, whether it is vertical or in horizontal direction during the incident and also during the reflection of the wave. So depending upon that, we will get the bands. So VV means here when the radio waves are passing through the atmosphere, the electric field is in vertical direction when it is passing towards the ground, and while reflecting the second part. V means it is also in vertical direction. If it is VH, while reflecting back, the electric field has changed direction to horizontal direction it is. So generally, for analyzing purpose, we consider VV polarization scheme. Okay, so we take always VV, vertical and vertical. It depends on the alignment of the electric waves. So if you double click on that, you can visualize the Sentinel-1 image that we have downloaded. Okay, this is how the image looks like before pre-processing. Now we need to apply pre-processing techniques. So what are they means? The first thing is we need to apply orbiter file. Okay, before doing the pre-processing techniques, I'll just explain what are the pre-processing techniques and why we are applying them. The first one is applying the orbit file. Why this orbit file is needed means, so when the sensor acquires that image, it will take approximate locations of the ground. So the location, whether it is x, y, z, or the velocity of the satellite or the timestamp, they are not exactly representing that particular location. They are approximated to some 10 meters. So, for analysis purpose, we need the exact orbit data. So, that orbit data will be stored in a file that is available in Snap. Snap will direct that from ESJ, the website that we have seen earlier. So when we give here the image, based upon the timestamp, it will take the associated orbit file from the ESJ website, and according to that, it will process the orbit data for this sentinel image. So we are going to do orbit file correction. Okay, that is the first pre-processing step. And after that, if there are any noise present in the satellite images, like thermal noise, we need to remove that. So the noise generally occurs along the borders, all the borders of the image. Like sometimes we see some vertical lines brighter in color like that. So those are noises which are to be eliminated for analysis purpose. Okay, so we need to apply corrections for that. And also sometimes due to while radar is passing reflected signal, when it is passing to the sensor and it is capturing, along with that signal, some disturbances that were created in the sensor instrumentation, they will also be captured along with the signal and presented in the data. So that noise should also be avoided. Okay, so that data will be provided by ESJ through some metadata files that Snap will take directly from ESJ. So when we apply that noise reduction, that all noise will be removed. Okay, is it clear? And then next pre-processing technique is calibration. So calibration, why we need to do calibration means, generally the Sentinel-1 image data, that will all the information will be stored in digital numbers. Okay, so for flood hazard analysis, we are analyzing two data sets, pre-flood and post-flood. So we perform raster calculations in the next processes. So with using digital numbers, we cannot do that processing. We cannot calculate that raster difference and all. So for that purpose, we convert that raw data into backscatter values. Okay, so calibration is performed based on calibration coefficients that will be provided, that are available in the metadata files. So when we apply calibration, they will take that calibration coefficients and they will convert the raw data to backscatter coefficients that will be useful for analysis purpose. So we are converting the data sets. Okay, so that is calibration purpose. And then next one is, we'll perform speckle filter. So speckle means, in an image, something like grain size. If you zoom into the image, if we observe some grain size dots in the image, which are due to, like for suppose, if the radar is target on a particular building or something, so if there are any trees or any objects near to that, when the signal falls on that particular aimed object, it will also fall on the nearby objects. And when the signals reflect back, all these signals will also reflect back from the plants or any vegetation or any other target that is available. They also reflect back from that. So when they all reflect back and go, so they will create some disturbance to the aimed object. So that's why we observe some grain sized disturbances in the image. To remove that disturbance is called speckle, and to remove that we apply speckle filter. Okay. So these are the pre-processing techniques that we apply in this software, Snap. After applying all this pre-processing, we will get the image that is best suited to perform the analysis. So now, all these 4 pre-processing techniques, 4 or 5, instead of doing each one, we can group them like a tool. We can build a model so that if we give the input data, all these pre-processing techniques, whatever we define, will be performed automatically, and the output will be stored where we give the location. Okay. So for that, if you go to tools, you will find graph builder. So you yourself creating like a model you are creating. What all the steps you need to perform, you are creating on your own. Okay. So here you already have read and write. Read is nothing but what data to read or what data to take as input. Write is something like output data. So in between input and output, you need to process all the pre-processing techniques. Okay. First of all, right click, delete this write. Okay. So we have this read file, which is nothing but the input that we have added. Now, to add the pre-processing technique, right click on this. Just simply right click on it and click on add. Okay. Radar. So first we discussed about orbit file. Okay. Simply right click on this window, add radar, apply orbit file. Okay. Is everyone following? So after that, similarly, add thermal noise removal, which will be in radiometric. So add radar, radiometric, thermal noise removal. Yes. Now I'll add all the pre-processing techniques here and I'll stop for everyone to complete. So radar, radiometric calibration. Next again, radar. The radiometric calibration. Speckle filter. In the radar, the bottom you will find speckle filter. And also one more pre-processing technique, that is terrain correction. So why we need to apply this terrain correction is, terrain is nothing but the elevation of the ground, right? So when the sensor passes to capture the image, the Sentinel-1 will have side-looking sensors. So it will pass the signal at some angle. Okay. So when it aims at some hills or mountain regions, the height, it may not capture exactly the terrain elevation data. So for that, if we give terrain correction and if we give externally the DEM of that location, DEM is nothing but digital elevation model. So for that particular area, if we provide the elevation data set externally, that is available in Snap, if we provide that DEM data, so it will auto correct if any distortions are there in the elevation values. Okay. So for that we will give geometric terrain correction. So these are the 5 pre-processing techniques. So after performing this pre-processing, we need to write the output file somewhere. So input output, write. So this is the whole process, starting from the data input data set to output. See, after this we need to connect it. Like starting from input data, what is the next step? So we need to connect everything using arrows. So if you right click, just connect graph will be there. If they are arranged properly, you can directly click connect graph. So everything will be connected automatically. Or otherwise you can manually connect it. See, if you place your cursor here, a red mark is appearing, right? So if you click on it, and you can drag to whatever post-processing technique that you need to perform. Okay. Right click, connect graph. So it will connect in order. whatever we've added in the window here, you can see them here. So you can change the parameters in this section. Okay. So first coming from read. So read is where you will give the input data. So as we have already added the data in Snap, so it will directly take that input data. Okay. So we are applying orbit file, auto download. It will be downloaded automatically. And then coming to thermal noise removal, as I said earlier, we'll mainly work with VV polarization. Okay, so you need to select VV here. So we'll take this VV band over here and work on removing all the noise or performing all the pre-processing techniques. And then calibration. By default it will be auto sigma band because we are converting digital number to backscatter values. Backscatter values are represented with sigma naught. So that is why it will be automatically selected. Speckle filter. We will be having different filters. Mostly Lee sigma and refined Lee will be used for flood mapping purpose. Coming to terrain coefficient, as I said earlier, you need to select the digital elevation model for terrain corrections. Okay. If you observe here, you have various options which can to select. Okay, here SRTM done. If you select 1 second and 3 second, two options are there. So 1 second means the resolution it varies, 30 meter resolution. If we select 3 second, it comes to 90 meter resolution. So we will select 1 second resolution, which will be automatically downloaded. And then here we will reproject the image. So if we click on this map projection, another window opens which says map projection. So we will convert it into QTM projection. So here WGS 84 means it considers the earth curvature into account. So geodetic system. Okay. So when we convert it into UTM system, it takes the earth curvature into a flat surface, which is good for analysis purpose. So that is why we will reproject it here. So if we click on it here, depending upon the location, see it will come zone 43. So the region specific. These are like local data. So we are converting the projection system from WGS 84 to UTM. Next is to write. Write means to save the file, that is so here you have to select, choose the directory where you are saving the files. Okay. If you want, you can change the directory and you can save wherever you need and click on run. It will take some time. Side looking sensors. So it will pass the signal at some angle. Okay. So when it aims at some hills or mountain regions, the height, it may not capture exactly the terrain elevation data. So for that, if we give terrain correction and if we give externally the DEM of that location, DEM is nothing but digital elevation model. So for that particular area, if we provide the elevation data set externally that is available in Snap, if we provide that DEM data, so it will auto correct if any distortions are there in the elevation values. Okay. So for that we will give geometric terrain correction. So these are the 5 pre-processing techniques. So after performing this pre-processing, we need to write the output file somewhere. So input output, right. So this is the whole process, starting from the data input data set to output. See, after this we need to connect it, like starting from input data, what is the next step? So we need to connect everything using arrows. So if you right click, just connect graph will be there. If they are arranged properly, you can directly click connect graph. So everything will be connected automatically, or otherwise you can manually connect it. See, if you place your cursor here, red mark is appearing, right? So if you click on it, and you can drag to whatever post-processing technique that you need to perform. Okay. Right click, connect graph. So it will connect in order. Here, whatever we've added in the window here, you can see them here. So you can change the parameters in this section. Okay. So first, coming from read. So read is where you will give the input data. So as we have already added the data in Snap, so it will directly take that input data. Okay. So we are applying orbit file. Auto download, it will be downloaded automatically. And then coming to thermal noise removal, as I said earlier, we will mainly work with VV polarization. Okay, so we need to select VV here. So we'll take this VV band over here and work on removing all the noise or performing all the pre-processing techniques. And then calibration. By default it will be auto sigma band because we are converting digital number to backscatter values. Backscatter values are represented with sigma naught. So that is why it will be automatically selected. Speckle filter. We will be having different filters. Mostly Lee sigma and refined Lee will be used for flood mapping purpose. Coming to terrain coefficient, as I said earlier, you need to select the digital elevation model for terrain corrections. Okay, if you observe here, you have various options which them to select. Okay, here SRTM them. If you select 1 second and 3 second, two options are there. So 1 second means the resolution it varies, 30 meter resolution. If we select 3 second, it comes to 90 meter resolution. So we will select 1 second resolution, which will be automatically downloaded. And then here we will reproject the image. So if we click on this map projection, another window opens which says map projection. So we will convert it into QTM projection. So here WGS 84 means it considers the earth curvature into account. So geodetic system. Okay. So when we convert it into UTM system, it takes the earth curvature into a flat surface, which is good for analysis purpose. So that is why we will reproject it here. So if we click on it here, depending upon the location, see it will come zone 43. So the region specific. These are like local datums. So we are converting the projection system from WGS 84 to UTM. Next is to write. Write means to save the file, that is so here you have to choose the directory where you are saving the files. Okay. If you want, you can change the directory and you can save wherever you need and click on run. It will take some time. So Okay. So meanwhile, you can save the graph. You need to repeat the same process for post-flood satellite image also. Okay. So all this process we have done for one satellite image before flood event, right? So the similar way you need to take the second image and process this pre-processing techniques. Okay, so you can save this graph for later use. File, save graph. Okay. You can save any location. For those who have generated the output file for this, you proceed with the post-flood satellite image. Okay. Once you save this graph, when you are doing it for second image, you can load that graph. Load graph, go to the location where you have saved, so that it will directly appear there. Okay. Open. Then it will come here. Give the input file. In the similar way, give all those like DEM and map projections, polarization, everything you need to assign and save the output to a location. That is for post-flood satellite image. Okay, those who have completed this, just proceed with the post-flood satellite image. Take a break for 5 minutes. Meanwhile, the process will complete. Okay. Snacks are pre-flood and post-flood satellite image pre-processings, right? Okay. You need to do for post-flood satellite image also. Okay. If anyone didn't complete for the post flood, let it be on a part. Okay, it will compute. So take that processed pre-flood satellite image. Okay. So if you click here and extend to bands, okay, you will see sigma naught VV. Sigma naught means because we have changed the calibration from digital numbers to backscatter values, it appears to be sigma naught. As we are working with VV polarization that we have chosen during pre-processing, right? In the thermal noise correction, we have selected VV only, not VH. So that is why it appears sigma naught VV. So that band is coming in the output file. So now here this image contains linear values, linear backscatter values whose range is too large. Okay, so now to minimize the range of values, we will convert them. So if you just right click them, linear to or from decibels. Okay, to minimize the range, we are converting this. Yes, convert. So this is the converted band. Okay, This is just to ease the analysis process. Okay, just right click on the sigma VV, then convert to linear to decibels. Okay. So generally the backscatter values range from -30 to +5. Okay, what does this backscatter represents means? If a radar signal hits a hard surface, then it reflects back with much intensity, right? With greater intensity. So it will have higher backscatter value. So from -35 to +5 is the range. Then the higher value would be like 0, -1 or +5 till +5. It is the higher range. So if the signal hits the water surface or any smooth surface, it will reflect with much lesser intensity. So it will give lesser backscatter value, which will be around -30, -20 like that. Okay. So here we have converted the range. So in this image, if we have any null data set, like null region, the region with no radar signal, okay, it will take some arbitrary value by default. Okay, that arbitrary value will create errors while processing them in the QGIS software. So to avoid that errors in the analysis part, if any null values are there, we are assigning a value like -35, which is out of the range. -35 like that, we will assign that value to the null points. Okay, that we will do in next step. So after pre-processing, we are converting the range of the satellite values. Okay, after converting the range to decibels, we are assigning some fixed number like -35 to the null points. So for that, go to raster band map. So whatever we are performing it, the output should be saved. So here we are giving a name to the output file. So my file, that one is output, like post-flood satellite image. So I am giving post-flood_VV. So if you are doing it with pre-flood image, give the name accordingly. And replace nav values or infinity results by -35. Okay, and then we need to give an expression. It's not like only -35. You can give any value that is out of the range, because it should not interfere with the particular range of -30 to +5. Okay. So to avoid the confusion, we are giving out of range value to be like -35. Okay. if you see the expression, if sigma value minus 100, so if it is within that range, then the same value will be retained in the image. If not, else we will assign a value 30 minus 35. Okay. So if the value is up to minus 100, we are keeping it the same value as it is. If it is beyond that, we are considering them as null values or no signal return values, and we are assigning value minus 35. Okay. So that expression means that. Click on OK. So the post-flood VV will be generated. So this is what we need for analysis purpose. Any confusion for anyone? So do it for the another satellite image also. So this is my pre-flood event sigma VV1. So first we are converting the values. So sigma VV underscore VB will come. For this you need to apply the expression. For that you need to go to raster band map and then give a name. That is the expression. Okay, shall we proceed further? After changing this calculation part, you need to save the product. Okay. So first select this pre-flood event, go to file and save product as. Okay, here go to file, save product as and save it in a location. Similarly, save the post-flood product also. Selected product, go to file, save product as. Okay, so now these two post-flood as for VV and pre-flood as for VV, these two are the final pre-processed images. So these two we need to take it into QGIS for analysis purpose. Okay, with this step the pre-processing was completed. So these are the saved products. Okay, if you open that, so this product you need to open in QGIS. Okay, .img file. So after saving the products, now open QGIS. one small suggestion to everyone. So when you are running with these files and images, everything should be located in a single location. If you change the locations and all, at the end they are not uploading into futures. We are facing problem with uploading them. Okay. Okay.
Might be there is a mistake where we have done this correction. Stand map.